Energy is the ability to do work. In the last section, we saw that if we compress or stretch a spring, it can store energy, and that stored energy could be released later. So I could have a spring that I stretch out, and when I let it go, it might pull up on an object. And when it does that, it would give that object what we call kinetic energy, or energy of motion. In order to give the object kinetic energy, it would have to exert a force over a distance. And that, of course, is work. So again, energy is the ability of a system to do work. So now what we're going to do is look at some different energy storage mechanisms and some different forms of energy. And the first one is the one I just mentioned, kinetic energy. That is energy due to motion. The shorthand for it is K. Sometimes you'll see it written as KE, but typically in AP Physics C, you'll see it written as K. And the equation for kinetic energy is 1/2 mv squared. And we'll do a lab where we derive that value. The next kind of energy we want to look at is gravitational potential energy. And gravitational potential energy comes from lifting something. It's energy due to position. So if I lift an object and then drop it, when I lift it, I give it gravitational potential energy, and when I drop it, that gravitational potential energy is converted into kinetic. The symbol for gravitational potential energy is U with a subscript of G to indicate gravitational, and the formula is mgh. I would just like to point out, if we zoom in on this a little bit, I'd just like to point out that UG equals mgh is also an expression of work. So this stored gravitational potential energy, work and energy are equivalent. And mg is a force, it's the force of gravity, and h is a distance. So really, this equation for gravitational potential energy is also an equation for the work done to lift an object a given height. At this point in the game, we've looked at springs already, but let's review. Elastic energy, or spring energy, is energy stored in an object by deforming it. So in the case of a spring, you could stretch the spring or you could compress the spring. There are other things like a bouncy ball that when you bounce it, it gets compressed at the bottom of the bounce. The energy stored is potential energy, so we're going to call it U. And then I'm going to write EL for elastic. Sometimes you'll see people write an S for spring. And the formula for elastic potential energy is 1/2 kx squared. And we derived that in a lab. We derived it by taking Hooke's law, F equals kx, and then if we have force and position, we integrate. Actually, let me back up a little bit here. If we integrate kx, in other words, if we find this area, we saw that area is equal to 1/2 kx squared. And see the previous notes for that. Finally, we have dissipated energy. And dissipated energy is energy that goes from the system to the environment. or we could say the surroundings. So in some situations, let's say I have a ball, and let's say I lift the ball. When I lift the ball, I give it gravitational potential energy. And then if I let it fall, that gravitational potential energy turns into kinetic energy. Let's say the ball is made of clay. When the clay hits the ground, the clay deforms, and the kinetic energy is gone. Where did it go? Well, it might have gone into a sound like a plop. It might have gone into some heat. In some scenarios, it might even go into light. It goes into deforming the clay. So all of those things are energy transferring to the surroundings. So typically, I just write E-dis to indicate dissipated energy. There's another way that we could dissipate energy. Let's say that I've got a brick, and I'm dragging the brick. And we'll say that we've got a normal force and a gravitational force and an applied force. And I'm dragging the brick at a constant speed so that the applied force is equal and opposite to a force of kinetic energy. In this case, I'm doing work because I'm exerting a force over a distance. I'm doing work, but when I stop pulling, the brick just stops. It doesn't keep moving when I let go. And so what's happening here is that the force of kinetic friction is dissipating all of the good work that I'm doing with my pull. In fact, the work done by friction is going to be the force of friction times the distance times the cosine of the angle between the force and the distance. But the angle between the force and the distance is 180 degrees, and the cosine of 180 is -1, so the work done by friction is a negative value. It's negative, Let me get a little more precise here. It is It's negative force of friction times distance. Okay, so the big takeaway from all of this is that we've got these different forms of energy. And just to review, we've got kinetic energy, energy of motion. We've got gravitational potential energy, that's energy due to physical position. We've got elastic energy, energy stored in an object. And then we can also dissipate energy or transfer it to the surroundings. And this is the first law of thermodynamics. It is extremely important. Energy is neither created nor destroyed. It merely changes forms, and it changes forms between those four forms. So let's take a look at some examples. What we have here is we've got some pies, energy pies. And the idea here is that the pie size stays the same. If you look at these circles, all these circles are the same size, and that's indicating that the amount of energy is the same. I'm going to label these 1, 2, 3, and I'm going to label the corresponding pie. At the very top here, a ball is held above the ground and then is dropped so it falls straight down. At the very top, all of the energy possessed by the ball is gravitational potential energy. That is energy due to height. At position 2, I'm a little less than halfway down, which means that more than half of the energy that the ball is gravitational potential energy, but some of it has been converted to kinetic energy because the ball now is moving. And finally, the instant before the ball hits the ground, this position 3 is the instant before it lands, all of the energy is kinetic. So in this scenario, if the object started, say, with 10 joules of energy, it still has 10 joules of energy at the end. It's just that it's changed to a different form. And in the middle here, perhaps it would have 6 joules of potential and 4 joules of kinetic. So it's not equally distributed, but the total is still 10 joules. Let's try another example. A wind-up toy is wound up, then walks across a table and comes to a stop. Once again, I'm going to number these and number my pies. So I'm going to assume that the wind-up toy is wound up, and at position number 1, the thing is walking. It has just begun to walk. So when we wind up the toy, during the wind up, we are storing energy as elastic potential energy. And once it starts walking, a little bit of it has turned to kinetic. And what happens is more and more and more of it turns to kinetic. So at position 2, it might not have very much spring energy left. Most of its energy might be kinetic. And then also some of the energy, kind of like we saw above, up here, we've got friction, right? Because the bunny isn't going faster and faster. We've got friction. So some of the energy is being dissipated. And when the thing finally comes to a stop, all of the energy has been dissipated. So all of the work that I did to wind up the toy has now been transferred to the environment through sound and heat. Here's another example. A super ball is dropped and bounces up and down. Do a pie chart for each position of the ball shown. Okay, so I'm going to number these. 1, 2, 3, 4, 5. And then I'm going to number the pie charts. So at the beginning, the ball has all gravitational potential energy. It has energy due to its maximum height. And at the bottom here, I don't know if you can see, this ball is actually kind of squished. And all of the gravitational potential energy, it went into kinetic energy right before the ball hit the ground. But now the ball has hit the ground and it's squished. And that squishing is actually elastic potential energy. Also, some of the energy is dissipated. The ball bounces back up, and I know that some of the energy is dissipated because when the ball bounces back up, it doesn't go as high as it did before. So at position 3, some of the energy has been dissipated, and there is gravitational potential energy, again, due to the new height of the ball. At position 4, we've got, again, elastic potential energy, but more of the energy has been dissipated. It looks like maybe even close, maybe almost exactly half, because look at this. At the 5th position, the ball is only about half, it's only about half as tall as it initially was. So maybe I would even make this a little bit, maybe I'd make this straight. And at position 5, half of the energy has been, half has been dissipated, and half is gravitational potential. One more example. An object rests on a coiled spring and then is launched upward. So this spring has been compressed. Somebody did work on this spring to push it down. So here we've got elastic potential energy. But I'm kind of getting this ahead of myself here. Let's number position 1, position 2, position 3, graph 1, 2, 3. So at this point, all of the energy is elastic potential energy because it's stored in the spring right here. Then In position 2, the object is about halfway up. So the elastic potential energy has been released, and now some of the energy is gravitational potential. It has some height, and some of it is kinetic. Looks like it's about half and half. And then finally, position 3, all of the energy has been transferred to gravitational potential energy. Okay, so what we've done here is we've just sort of practiced thinking about the forms of energy, again, kinetic, gravitational potential, elastic, and dissipated, and how they change form, how it's neither created nor destroyed, but it merely changes form. What I'm going to do next, when I solve the next couple of problems, is I'm going to use the formulas here, the formula for kinetic, gravitational, elastic, and dissipated, and I'm going to solve for some actual numbers. So, example 3, Freefall Freddy. He's in an elevator. He's going from the ground floor up to the 5th floor. Each floor is 4 meters apart. Freddy weighs 750 newtons. What is Eddie's gravitational energy on the 5th floor? Okay, well, first of all, his height is 4 meters times 5 floors, or 20 meters. Gravitational potential energy is mgh, and mg is his weight, so that's 750 newtons, and then the height was 20 meters, and when I multiply those together, 750 times 20, I get 15,000 Newton meters or joules. Suppose the elevator cable snaps. What is Freddy's kinetic energy right before he hits the ground? So the idea here is that the gravitational potential energy at the top is the same as his kinetic energy at the bottom. So he started at the ground floor, he got lifted up to a certain height, and he had gravitational potential energy, and then right before he hits the ground, this is getting a little gruesome, these two values are equal. The gravitational potential energy at the top and the kinetic energy at the bottom are equal, which means that his total amount of energy is the same. It's 15,000 joules. We can use this to find his velocity right before he hits the ground. So if we say that gravitational potential energy at the top equals kinetic at the bottom, we can make a substitution and say mgh equals 1/2 mv squared. And I'm going to go ahead and do a little derivation here because this is very useful. We can divide both sides by m, and I'm going to solve for velocity. So now I'm going to multiply both sides by 2. So I'm going to say 2gh equals v squared, or v equals the square root of 2gh. Turns out his mass doesn't matter at all, and we know that also from our work in kinematics. So I'm running out of room, so I'm going to go to the left here. So to find his final velocity, I'm going to take the square root of 2 times 9.81 times 20. And when I do that, I get 19.8. And that is meters per second. Okay, one more example in this section of our notes today. A car is being loaded onto a truck by pulling it up a plank inclined at 20 degrees above the ground. The plank has a length of 6 meters and the car has a mass of 1,500 kilograms. What is the increase in the car's gravitational energy? I'm going to make a little sketch here. I'm going to draw the plank, and there we go. We know that this is 20 degrees, and the plank has a length of 6 meters. So in order to find the change in gravitational potential energy, I need this change in height here. So I'm going to use trigonometry to find it. I've got a right triangle. I've got the hypotenuse of the right triangle. H is the opposite side, so I know that the sine of 20 equals h over 6. So I will solve that with 6 sine 20, and I get 2.05. And then to solve for gravitational potential energy, I'll solve mgh. So that's 1,500 times 9.81 times 2.05. So that's 30,196, or about 30,200 joules. How much energy is lost to friction, heat, and sound if it takes 90,000 joules to get the car to the top of the ramp? So let's imagine for a second that we've actually got a car here. So there's my car, and I'm going to pull it up this ramp. If there were no friction, at all, it should take me 30,200 joules to get that thing up the ramp. But it turns out in this example, there is friction. In fact, there's so much friction, it doesn't take me 30,000, it takes me 90,000 joules. So that extra 60,000 joules is energy that is lost. It's not really lost, but it's transferred to friction, heat, and sound. So I just have to find the difference. 90,000 minus 30,200 would be 59,800 joules. And that concludes our examples for this section 5.2.